Moment distribution method. This method is used to analyze statically indeterminate structures like fixed beams, continuous beams, and portal frames. See part of the continuous beam. The span AB. Subjected to external loadings. We have to calculate final end moments at supports A and B. The final end moment at any support R. Algebraic sum of end moments generated may be of the following reasons. Due to fixed end moments developed because of rigidity of supports. Due to release in fixity at supports which creates slopes. Due to sinking of supports. And due to lateral deviation of unbraced ends or joints. Let us study each of the reasons step by step. 1. Fixed end moment due to fixity of the support. As fixity of support do not allows bending moments to create rotations or slopes at end, the resisting moments are generated to held or restrain rotations at supports. These are denoted with M-AB and M-BA respectively. One should remember that when we convert fixed end with full rigidity to continuous end with partial rigidity, or convert to simply supported end with no rigidity, the slopes are generated more and more at that end, and carry-over factor to far end also increases. Next step is to release fixity at support A. Maintain the fixity at support B. To produce a slope IA at end A, we need a clockwise moment equal to 4 into A into I into IA upon L. As far end is fixed support B, the carry-over moment will be clockwise moment and equal to half the moment applied at end A. That is 2 into A into I into IA upon L. Release fixity at support B. Maintain the fixity at support A. To produce a slope IB at end B, we need a clockwise moment equal to 4 into A into I into IB upon L. As far end is fixed supporter, the carry-over moment will be clockwise moment, and equal to half the moment applied at end B. That is 2 into A into I into IB upon L. Maintain fixity at supports A and B. If support B sinks with deflection delta downwards with respect to support A, to maintain zero slopes at ends A and B, the anti-clockwise end moments equal to 6 into A into I into delta upon L squared will be generated at both supports. Sign conventions. Take clockwise moment as positive moment, and clockwise slope as positive slope. If right support sinks downward with respect to support at left, take deflection as positive deflection. If top end moves to the right with respect to bottom end, take the deviation as positive deviation. Stiffness of member. Stiffness of member S of uniform cross-section, whose far end A is fixed or continuous, and moment M is applied on simply supported near end B. The moment required to produce slope IB at end B is M. M equals 4 into AI into IB upon L. The carryover factor or moment at end A is half the applied moment M at end B, and is of the same order as that of the applied moment. The stiffness of member is the moment M required at end B to produce unit slope IB equals 1, without translation at end B. So for IB equals 1, the moment required is M equals S equals 4 into AI upon L, known as stiffness of the member AB. Stiffness of member S of uniform cross-section, whose far end A is hinged or simply supported, and moment M is applied on simply supported near end B. The moment required to produce slope IB at end B is M. M equals 3 into AI into IB upon L. The carryover factor or moment at end A is 0, as there is no resistance generated against formation of slope at end A. The stiffness of member is the moment M required at end B to produce unit slope IB equals 1, without translation at end B. So for IB equals 1, the moment required is M equals S equals 3 into AI upon L, known as stiffness of the member AB. Distribution factor. Distribution factor for a member meeting at a joint is ratio of the stiffness of the member to the total stiffness of all the members meeting at the joint. Take a continuous beam ABC. Let support A as hinged support. Support B is continuous support, and support C is fixed support. Span AB is of length L1. Span BC is of length L2. Let flexural rigidity is same for both spans and is equal to AI. As can be seen from diagram, two members BA and BC are meeting at a joint B. The far end for member BA is hinged, and far end for member BC is fixed. So stiffness of member AB is S1 equals 3 into AI upon L1, and stiffness of member BC is S2 equals 4 into AI upon L2. Total stiffness will be S equals S1 plus S2. S equals 3 into AI upon L1 plus 4 into AI upon L2. So, distribution factor for AB is D1 equals S1 upon S equals 3 into AI upon L1 divided by 3 into AI upon L1 plus 4 into AI upon L2. Distribution factor for BC is D2 equals S2 upon S equals 4 into AI upon L2 divided by 3 into AI upon L1 plus 4 into AI upon L2.
For complete course and step-by-step illustration, please subscribe full course on Structural Analysis and Design app. Also subscribe YouTube channel Maatrixx Digital Solutions. Thanks for watching.